Hello everybody, welcome back to another CIV E 398 assignment tutorial. In this assignment tutorial, we're going to be covering assignment 6, question 4, which is the last question of assignment 6, so that's nice. But it's a pretty long question or a more in-depth question, and what's nice about this question is it takes basically everything we've learned thus far in continuum mechanics and wraps it up into one nice little package. And from here, as we're going to see, it's going to be a little bit complex. So we're going to have to use Mathematica to solve this question. You don't really have to, but it's heavily recommended that we use Mathematica. But don't worry, at the end of this, I will give you guys a nice little Mathematica tutorial. And that's why this video is a little bit late. I wanted to go through both seminars, see what you guys are asking when it comes to Mathematica. That's when I create this video. It's as complete as possible. Now, I'm sure I'm going to get a couple more questions at the end, but that'll be fine. I'm happy to answer any of the questions that you guys may have. All right, so question 4 says the position functions of a 2D steel plate are given by, and they give us small x1 and small x2. And that's how you know this question's really taking everything that we know, because position functions, that was a couple weeks ago, but yet they're coming back. But we know that position functions are nice because they can give us the strain tensor, and that's going to be kind of the main goal of this question. So it says assume that the steel is a linear elastic isotropic material with a Young's modulus of 200,000 units and a Poisson's ratio of 0.3. However, remember, as I said, we're going to go to Mathematica. In Mathematica, it's better to express things as fractions, so it's the same as saying 3 over 10. It says if the length L and height h of the plate are 4 units and 1 unit respectively, and the steel is in a state of plane stress, so that's going to be definitely a big one, state of plane stress, determine A, the strain tensor in terms of x1 and x2, B, the stress tensor in terms of x1 and x2, C, the von Mises stress at the center of the plate, and D, the contour plots of sigma 1, sigma 2, sigma 3, as well as sigma von Mises over the entirety of the plate. So if we look at this question, it actually boils down to basically two different things. The first one is the strain tensor, and the strain tensor is going to be the first challenging problem that we're going to encounter because we're not given any of the tensors. You know, if we have the stress tensor, we can find the strain tensor, or in the other cases, we're already given the strain tensor. However, we're given position functions. Now, as we recall, we can easily find the strain tensor using these position functions, but it's a little bit of work, and being that we did this a couple weeks ago, you guys may have already forgot, so we're going to run down how to go through that again. The second thing that we're going to want to find, of course, is the stress tensor. Now, if we have that strain tensor and we know that this is an isotropic linear elastic material, we know that we can find the stress tensor. And what makes this even easier is we are told that this is a state of plane stress. Therefore, we can actually convert from strain to stress even simpler because instead of needing that ugly 6x6 matrix, we can simplify down to a 3x3. And that's basically the question, because if we have that stress tensor looking at part C, well, the von Mises stress can easily be calculated from that stress tensor because we know the von Mises stress is a function of sigma 1, sigma 2, etc., which we have in the stress tensor. And finally, part D, where it's asking for the contour plots of all the sigmas. Well, again, if we have the stress tensor, we have sigma 1, we have sigma 2, and 3, etc. So the main question comes down to, okay, what is going to be the strain tensor, and then what is going to be the stress tensor? So for right now, for fun, let's just say that we know the strain tensor. Okay, we have the strain tensor, it's in our back pocket, we're good to go. And from that, we know that we can find the stress tensor if we know that strain tensor. And luckily for us, the question says that it's in a plate of plane stress. Now, if it's in a state of plane stress, what that means is that sigma 1, sigma 2, and sigma 3 are all going to be equal to 0, which is great because then we can simplify our elasticity tensor, so that's that big chunk in the middle, into the following form. So instead of 6x6, we see that it's now simply 3x3. Not too bad. So what the input is going to be components from our strain tensor, which we can find out, and then this will give us the components of our stress tensor. Now notice how we're only given 3 components of our stress tensor, but our actual stress tensor has 6 components. But remember that under plane stress, sigma 1, sigma 2, and sigma 3 are equal to 0. So after we do this calculation, we'll have all the components of our stress tensor. And if we have those components, then we can start finding the von Mises stress, because the formula for the von Mises stress is just a function of all those components of the stress tensor. And if we know them all we have to do is substitute them in nicely, we can find our von Mises stress. So in essence, what I'm trying to really hint at is we can do everything that we need to do very simply if we have that strain tensor. But how do we find that strain tensor? So again, the key to this question will be that strain tensor. So recall that we can determine the strain tensor previously using displacement functions. And we did this a lot in assignment number 4. So if you guys want some extra reference material, we can go back to assignment 4 for reference. But again, I will show you how to do it all right now. So the key here is that we can find the strain tensor using displacement functions. However, we are actually given position functions. So displacement functions, those are the u1, u2. However, we're given x1, x2, which are position functions. But luckily for us, there is a very nice relationship between the displacement and position functions. And the following relationship is as follows, where u is equal to x minus big X. So the displacement function is simply the position function minus big X. So once we know these displacement functions, then we can do something special by finding something called the displacement gradient, which is the true key to finding the strain tensor. So displacement gradient can be determined by taking all those partial derivatives of the displacement functions. So you're saying, wait, what was that, Clayton? I kind of forgot what that is. Well, that's this, where nabla u, or the displacement gradient, is equal to the partial derivatives of all the displacement functions. So if we look at that first row, it's going to be the partial derivatives of the displacement function u1 with respect to x1, and then with respect to x2, and then with respect to x3, and so on for displacement function 2 and displacement function 3. Now, luckily for us in our question, we only have u1 and u2. There is no displacement function u3. Therefore, we only have to take the partial derivative 4 times instead of the 9 times as shown in the formula. But since we're doing it in Mathematica anyways, it doesn't really matter too much. Now, if we have this nabla u, or if we have this displacement gradient, then we can find something called the strain tensor, which is again what we want. And the formula is very nice for the strain tensor, or the small strain tensor, is simply 1/2 multiplied by the gradient of u plus the transpose of the gradient of u. So all we need to do is find the strain tensor is have that displacement gradient, which we can solve for above. So if we were to wrap up this question into steps, so just a couple nice steps, we have step number 1, find the displacement functions. Right now we have the position functions, but we know if we were trying to find our displacement gradients, we need displacement functions, not position functions. Once we have those displacement functions, we can then find the displacement gradient, no problem. And then from that displacement gradient, we can calculate the strain tensor. So that's what I kind of call part 1 of this question, finding that strain tensor. And as you guys will see in your question, it's basically part A of the question. By the end of part A, it'll ask you what are the components of that strain tensor. Now, once we have that strain tensor, we can use our elasticity tensor under the plane stress conditions to determine the stress tensor from that strain tensor. So it's really nice and easy. And with that stress tensor, we can calculate everything else that we need. So part C of the question says the von Mises stress. Well, since I have my stress tensor, the von Mises stress is no problem. And then finally, it also wants us to plot the components of the stress tensor. And just like before, if I have the stress tensor and I have all those components, well, I simply just have to contour plot them in Mathematica, piece of cake. So just one little note to finish off with is since we have position functions, so we have basically a bunch of x1s and x2s, x1 squared even, stuff like that, it's best to use Mathematica. Again, you guys can easily solve this question by hand, but this is definitely more a Mathematica driven question, and it'll make your guys' lives a lot easier. And because of that, I know Mathematica can be a little challenging sometimes, so what I'm going to do is try and provide a little tutorial on that. So let's jump into Mathematica. Alrighty guys, welcome to Mathematica. As you guys can see on the left-hand side, we have our Mathematica notebook. So this is where we're going to be doing all of our calculations. And then on the right-hand side, just for reference, I wanted to show you both the parameters that were given, as well as some useful equations that I'm going to be throwing into Mathematica. I find if I don't really show you guys the equations and I were just to type them out, it's very hard to understand what exactly I am typing out. So I thought, you know what, maybe it'd be nice if I had the equations on the side of the screen, make our lives a little bit easier. So all I did right now so far is I defined basically the steps that I told you guys. Remember, I told you guys that this question can be simplified into a number of steps. I wrote down the steps and we're going to figure out how to solve each one. But then I also included A, the known parameters. So we know that the Young's modulus was 200,000 and we know that the Poisson's ratio was 0.3. So I have EM as 200,000 and then I have V as 3 divided by 10. Again, I want to try and keep it in that fraction component. Now, a lot of you guys asked me during the seminar, and this is why I'm glad I did the seminars first, is why did you do EM instead of just E? Well, E in Mathematica is actually already defined. So if I were to go E and everything else is suppressed and run it, E is actually that right there. It's actually a defined function, so if I try and store 200,000 into E, we're going to have a lot of problems. And the way I can tell that it's actually something is it's already black. So notice how if I go EQ, it turns green. If I go EP even, it turns green. However, E by itself is black. It means it's already defined. I have to pick a different variable. So that's why I put EM, which is just going to be, in my head, the elastic modulus. It's still short and sweet, which is what I want. However, it's an undefined variable, so I can define it as 200,000. V happens to be undefined, so therefore I just threw in V, even though the actual Poisson's ratio is considered nu, the Greek letter nu. Now, what I also did is I defined my two position functions, small x1, small x2. Now, these are much simpler than what you guys are given. You guys will have a bit more complicated position functions, but I thought, you know what? For the sake of tutorial, I'm going to give just nice, easy position functions. Then we can track along what's going on a lot easier. So far, again, I have the parameters, and then I have my two position functions. So this is exactly what you guys will have at this step. Now, when we're talking about this question, we said that the first real thing that we're going to want is that strain tensor. So we want to come down here and we want to figure out what that strain tensor is. So that's going to be part A. Well, we said the first thing that we need to do is find the displacement gradient. In order to find that displacement gradient, I need to find the displacement functions. But there was a very nice formula for those displacement functions. So what I like to do, because I don't want to repeat the process a bunch of times. If I have x1 and x2, I don't want to have to solve for u1 and then solve for u2. I'd rather just do it as a whole. So the first thing I always like doing is I like defining my position functions as one single vector. So instead of x1 and x2, I'm just going to go x is equal to, and this will be x1 and x2. So now if I run this right here, I have a vector, and the first entry of this vector is my small x1, and my second entry of this vector is small x2, which is exactly what I want. And then I'm going to find a second vector, which we call x. And x is going to be the same thing, except it's going to be big X1 and big X2. And I'm just going to try and make this somewhat nicer. All right. So if I run this, again, my old entry, big X1 and big X2, which is exactly what I want. So now I got x and big X as vectors. Therefore, I can find the displacement function u also as a vector. And we knew from our slides that u is going to be simply x minus big X. So what I do here, if I were to run this, I see that I have two components. So this right here, this would be my u1, and then my second component right here, this would be my u2. So now I have my two displacement functions calculated very simply. If I didn't put them as vectors, I can still calculate it as u1 is equal to small x1 minus big X1, and then u2 is equal to small x2 minus big X2. I'm just trying to save myself a little bit of space. This is how I do it. So that's how we find the displacement functions. As you can see, this section, it's pretty small, nothing really happening going on because most of it's already defined above. Now, the displacement gradient. This is going to be the trickiest part of the assignment for most of you guys, is finding this displacement gradient. So typically when I'm doing code, I define the displacement gradient as grad u. You guys can define it as whatever you want. This is just how I personally define it. And the problem is if we look at our equations over on the side, so this right here, this is going to be our displacement gradient equation. We're taking a bunch of partial derivatives. Now this is where things get tricky. So we're not just taking one partial derivative. For example, if I wanted the partial derivative of u1 with respect to x1, that's no problem at all, because we know in Mathematica, I can do a partial derivative using the d function. So since it's a function, it's going to have those square brackets. And the first thing is going to be, what is the function I'm taking the derivative of? So this would be u1. And then the second thing is, what am I differentiating with respect to? So this would be x1. So this would be this component right here, the differential of u1 with respect to big X1. So if I were to run this, no problem at all. I can see that I have my partial derivative as 2x1. The problem that we do have is that's just this partial derivative right here. However, as I mentioned, we're going to need four partial derivatives. We need partial u1 with respect to big X1. We need partial u1 with respect to big X2. We need partial u2 with respect to big X1. and then partial u2 with respect to big X2. So the question becomes, can I do this all in one simple manner? And the answer is yes. I can use something in Mathematica called the table function. So I'm going to go table, if I could spell it, of course. And again, since it's a function, it's going to have both of those square brackets. And basically, the table function takes what you want to do, and then you want to find the limits of what you want to do. So I'm going to put in two brackets because we're going to deal with this. So the table function is exactly how it sounds. It basically returns us with a table. And if we were to look at this formula for nabla U, or the displacement gradient, it's basically a table. Here's our first entry, here's our second entry, and then we go down, and here's our first entry of the second row, and here's our second entry of the second row. So that's why we're using this function, because it's very nice. And all we have to do is define the rows and define the columns as I and j. So if I'm going through here, I say, okay, well, I is going to be my rows. So what I'm going to do is I'm going to take the partial derivative of ui. So in this case, if I was looking at the first row, it would always be u1. If I was looking at the second row, it would always be u2. Or the third row, always be u3. And then I'm taking that with respect to xj. And j is going to be the column. So if I were to go I is equal to 1, j is equal to 1, well, that'd be partial u1 with respect to big X1. Now, if I keep I is equal to 1, but then go j is equal to 2, well, that's partial u1 with respect to x2. So that's what's going to be what we define at the end here in this table function in these two columns. We're going to have to define what I and j exactly is. So I'm going to put two squiggle brackets right here. And the first one, we're going to say, all right, well, we know that we're dealing with I. We're going to start at 1. And the second thing is, what do we end up with? Now, this is very misleading if we look at the equation here on the right, because we have 1, 2, 3, and then if we look at the rows, we also have 1, 2, 3. So a lot of students are putting 3. However, we have to remember that right now we don't have a u3. We're dealing with 2 dimensions, so we have a u1 and a u2. So I come down here, I say, all right, well, I got u1, I got u2, and I don't have u3. So technically, I don't actually go to u3. I only go u1 and u2. So my final thing here would actually only be 2. It wouldn't be 3, it would be 2. Now, if I had a three-dimensional case where I do have u1, u2, and u3, then yes, this would be a 3. However, we're dealing with 2 dimensions. We only have 2 row entries that we're interested in. And the same thing goes for j. So we know that j starts at 1, and j will go to 2. Because again, we don't have that partial x3. There's in no case that we have an x3 that we need to deal with. So what happens is we go from 1 to 2. Now, if I were to go 3 by accident, Mathematica is kind of smart in that it says something's wrong, Clayton. You did something wrong. Because if I look, I get a bunch of errors. And the error says part 3 of this does not exist. So remember, I'm taking the components of a vector. And if I look at my vector x right here, it has 2 components. So if I put in 3 here, it's saying that I want to take the third component. But there is no third component. So therefore, if we try and do 3, something will go wrong. Now, if we did have x3, and we had a u3, well then we do have that third component, things work out. However, we only have x1 and x2, so therefore we can only do 2. So if I change those back to 2, which is how it should be, and I run this now, no problem at all, it gives me my gradient of u. So it doesn't look like it because it's all written in kind of that linear form, but if I were to do this in matrix form, we can quickly see that our gradient of u is indeed a matrix. So the first entry was 2x1, the shear entry here, or I guess entry 1, 2 is 1 divided by 200, and same for entry 2, 1, and then entry 2, 2 is 2x2. So now we have our gradient of u, piece of cake. And again, the key here is using that table function to iterate through the different u's and the different x's. All right, so that's not too bad, but again, this will be the hardest part. After here, it's smooth sailing. So the next part I said is, okay, well, with that gradient of u, or that displacement gradient, we can find our strain tensor. So if we look down here in our useful equations, we know that our small strain tensor is simply 1/2 the gradient of u plus the transpose of the gradient of u. So what I can do is I can go strain tensor, so I'm putting a t here. I'm saying, all right, well, this is going to be 1/2, so I'm going to go 1 divided by 2, multiplied by the gradient of u, so gradient of u plus the transpose of the gradient of u. So remember that in Mathematica, when we're dealing with transpose, capital T, transpose, and we know that we did it right if it goes black. If I were to put 2 e's by mistake, it turns something blue, which means it's undefined. However, If I write it correctly, it turns black. It means, yes, this is a function. And functions, again, have those square brackets. So I'm going to put the transpose of the gradient of u. So I'm going to run it, and I can see I have a nice 2 by 2 strain tensor. So if I put it in matrix form, we can actually see this a little bit nicer. Here's our strain tensor at the beginning. So that's good to go. Looking pretty nice so far. But now we have to realize one specific thing. When we're dealing with this strain tensor in 2D, or more specifically, when we're dealing with plane stress, we have to keep in mind that there actually is a strain component 3,3. So what I'm going to do is I'm going to calculate it. So I'm going to go strain 3,3 is equal to, and if I look down below, I say, okay, well, my strain in the 3,3 direction is equal to negative V over E. Well, that's perfect because I have them defined above right here. Multiply, oh, wait a second, sigma 1, 1 plus sigma 2, 2. So right now, in its current state, I actually cannot find the complete strain tensor because I don't have enough information to solve for epsilon 3,3. So what I'm going to do is say, okay, well, it was a nice try, but I can't quite get there yet. What I'm going to have to do is use the relationships between the stress and the strain to figure out those stresses before I can finalize figuring out the strains. So the first thing that we have to keep in mind is when we're looking at these type of formulas for plane stress, our strains as well as our stresses are in vector form. But again, if I were to unsuppress this and put it in my form right now, I have a tensor. I don't have a vector, I have a tensor. So the first thing I'm going to have to do is say, okay, I have a tensor, but I have the components of the vector, so I can create a strain vector, which I'm going to go strain V. So above strain T, strain tensor. Below I go strain V, which is strain vector. And if I look at the components, it's a simple vector with 3 components. It's going to be epsilon 1, 1, epsilon 2, 2, and epsilon 1, 2. So what I can do is, all right, it's a vector, so I'm going to do my squiggle brackets. And inside, I'm going to have epsilon 1, 1. So that'll be the 1, 1 component of my strain tensor. So I go strain T, double square bracket, 1, 1, and the double square bracket, comma. So again, that's the first component. The second component is epsilon 2, 2, so I can get that from my strain tensor as well. And the final component is going to be epsilon 1, 2, so I can go strain 1, 2. Now here's the problem that a lot of students are going to have, and this will cause a lot of mistakes. If I were to run this right here, as we can see, no problem at all. I want 3 components. I have 3 components. So if I were to throw this in matrix form, to really simplify what we can see, we have 3 components. So this looks like it's correct. We have to keep in mind, though, that when we're dealing with our strain vector here, we have a 2, and I'm going to highlight it here, or change its color. We have this 2 in front of our shear strain. So when we actually define our shear vector, the epsilon 1, 1, no problem. Epsilon 2, 2, again, no problem. But when we get to epsilon 1, 2, or that shear strain, we actually have to go 2 times whatever that component is. So now when I run it, we can see that it actually changes the value, and that's going to be very, very important for us. So right now I have my strain tensor, and then I made this 3-component strain vector. Now, in order to convert, we see that we need the elasticity tensor in the center there. But if we look at this elasticity tensor, it has a coefficient 1 divided by E. Well, we have that, that's no problem. And then we have a tensor full of the Poisson's ratio V, and nothing else. And if we look at that, we say, well, we know that too. So to define this, this is going to be nice and easy. So I'm going to go ET, which is basically elasticity tensor. I'm not talking about the alien here. And I'm going to define, first of all, the coefficient. So that's 1 divided by E. So I go 1 divided by, and I have E defined as EM. So if I look up at the top here, I have my E as EM. And then I'm multiplying this into a 3 by 3 tensor. So I do the squiggle brackets, and then I want to put 3 sets of squiggle brackets. So each one of those is the row of this tensor, and I just simply go down the rows. So looking at the first row here, I have 1, I have negative V, and then I have 0. So I'm going to go 1, comma, negative V, comma, 0. Piece of cake. Go to the second one. Well, now I got negative V, 1, and then 0. So I go negative V, comma, 1, comma, 0. And then I ended off at the very end here where my last row is 0, 0, and then 2 times 1 plus V. So I'm going to go 0, comma, 0, comma, 2 multiplied by 1 plus V. Now, if I were to just throw this in matrix form just for fun, I can see that I have my nice elasticity tensor here defined below. And what's nice is since I have V and EM defined all the way above here, I can see that it's already defined in this nice form, looking pretty sexy if I do say so myself. Now, if I were to go V is actually equal to 0.3, which is given in the question, instead of the fraction. If I were to run this now, I have a bunch of decimal numbers, which is going to be a problem because when you look at your assignment, it explicitly says that it wants things in fractions. It doesn't want decimals. So this is why we want to try and keep all of our entries in fractional form. So instead of 0.3, I'm going to go simply 3 divided by 10. That way, when I get my elasticity tensor, everything's in terms of fractions, no problem, looking pretty good. So that's the elasticity tensor, looking good. And remember that if we look at this formula, we're saying, okay, well, we want the stress components right here. So it's, oh, wait a second. I have this formula in terms of what the strains are equal to. So a lot of people go, oh crap, I picked the wrong one, and I've done this so many times. Dr. Adib is very nice in his website where he gives you both what the strains are equal to, but then he gives you what the inverse and what the stresses are equal to. Now let's say you guys picked the wrong one like I did, where I'm trying to solve for these over here, all these stresses, but I wrote the formula wrong, where I really wanted the stresses on the left side and the strains on the right. Well, that's no problem at all, because remember that we can actually manipulate matrix multiplication. So if I'm looking for the stresses, I'm going to go stress and I'm going to go V, because remember, we're looking for a stress vector at this point, not a tensor. This is going to be equal to, and all I have to do is move all this, so all this, over to the left-hand side. Now, when we're doing the matrices, this is simply going to be the inverse. So my stress vector is actually going to be the inverse of ET. So inverse is a function that's nicely defined in Mathematica. And then I multiply this by my strain vector. So I'm going to go strain vector. And what I'm going to do is I'm going to throw this in matrix form so we can see what it looks like. And you're going to go, oh, wait a second, something's wrong here. And I'm actually going to suppress the strain vector really quick so we don't have to see it. This is what we get for our stress vector. And as you guys will see, something is very wrong because we're expecting this right here, or I guess just this, just a vector, 3 components. What do I have here? I got a matrix of 3 by 3. I'm not expecting that. Again, I should be getting a vector. And this has to do with matrix multiplication. Remember that in Mathematica, when we multiply 2 matrices together, we don't use the star symbol. That's for scalar multiplication. So what we're doing is we're actually going to use the period. So we're doing the inverse of ET dot, or not dot as in dot product, but period, which means the matrix multiplication times the strain vector. So now when I run it with the period instead, as I can see, I have a stress vector full of 3 components. So we got the first one, we have the second one, and then we have the third one. So it's looking really good. And as we can expect, they are functions of, it's hard to see here, but they are functions of x1 and x2, which is what the question kind of hints at. So we're good to go. So now that we have our stress vector, of course, we want our stress tensor. So we're going to go stress T, so tensor. And we know that's going to be a tensor with 3 rows. So I'm going to go 1, 2, 3, and I'm just going to fill out the rows. Nice and easy. So our first component of the stress tensor, sigma 1, 1. Well, if we look at our stress vector that we have, that's their first component of our stress vector. So what I can go is I can go stress V, 1, and just 1, because it's a vector, it's not a tensor. So we got stress V. Well, I know that if I'm moving along, the second component is going to be sigma 1, 2. And we can see that that's actually the third component of our stress vector. So I can go stress V, 3. And then finally, we have sigma 1, 3, but we're under plane stress, so we know that sigma 1, 3 is simply going to be 0. Now, coming down to the second row of our stress tensor, we know the first entry is going to be sigma 1, 2. Well, we already said that sigma 1, 2 is simply going to be the third entry of our stress vector, so I'm going to go stress vector 3. The second entry in our row is going to be sigma 2, 2, which if we look at our vector is actually the second entry in our vector. So what I can go is stress vector 2. And then finally, our last entry is going to be sigma 2, 3. But again, under plane stress, sigma 2, 3 is actually equal to 0. Finally, the last row of our stress vector is going to be sigma 1, 3, which we said is 0 because of plane stress. Sigma 2, 3, which again is 0 because of plane stress. and then finally sigma 33, which again under plane stress is equal to 0. So if I were to run this in matrix form now, I get this right here, and this would be my answer to, I guess, part B of the question, where it's asking for my stress tensor. All right, so not too bad so far. The last thing that we're going to want to go revisit is the, I'll just say, modified strain tensor. So remember that we couldn't find the complete strain tensor before because we needed this little doodah down here, epsilon 33, but we couldn't find it because we needed sigma 11 and sigma 22, which we didn't know at the time. Luckily for us now, we can find epsilon 33 because we now know sigma 11 and sigma 22. So as we can see, it's going to be negative V divided by E, so I'm just going to put that right there, multiplied by sigma 11 plus sigma 22. So I can get these either from my stress tensor, or I can say, all right, well, they're also in my stress vector as components number 1 and component number 2. So what I'm going to do is I'm going to use the stress vector. So I'm going to go stress vector 1 plus stress vector 2. So it's just taking the first component of my stress vector, which is sigma 11, and adding it to the second component of my stress vector, which is sigma 22. If I were to run that right here, I find that it's going to be this right here. A little bit gross, but it is what it is. We can do full simplify later on to make it a little bit cleaner, but actually let's you know what, might as well, we got time. Let's check out what the full simplify function does to this bad boy right here. So I'll just put the full simplify around it. Oh, as we can see, it simplifies into negative 6 over 7 x1 plus x2. So again, use that full simplify. It'll make things a lot easier for you. So I'm going to get rid of it. For now, I'm going to say, all right, well, now that I know sigma 33, I can define my strain tensor in a more complete form now. So what I'm going to do is I'm going to say, all right, well, it's going to be a tensor, so it's going to have 3 rows, and no, p does not exist in any one of those rows. So the first one is going to be the first component of the strain vector. So if I go up here, I can go, all right, well, this will be the strain vector 1, and I'll put that there. The second component will be the shear strain from the strain vector. So I'm going to go strain vector, and wait a second. If I look at my third component in my strain vector, it's actually multiplied by 2. So when I put it in this third component, if I want the actual strain epsilon 1, 2, I got to divide by 2. And that's again because if I'm taking that third component, I'm taking all of this. So I'm taking the 2 times epsilon 1, 2. So if I'm using the strain vector, I'm saying, all right, well, I'm going to take that whole component, and then I'm going to divide by 2. And again, epsilon 1, 3 in this case will be 0. Nice and easy. Moving on to the second row, the first thing that we start off with epsilon 1, 2, well, we just defined that above. Well, that's going to be the strain vector's third component divided by 2. Then we go to epsilon 2, 2. Well, that's going to be the second component of the strain vector. And then finally, epsilon 2, 3. Well, that's just going to be 0. Moving on to the third row, epsilon 1, 3 and epsilon 2, 3 are both equal to 0. So 0, 0. But then we know that epsilon 3, 3, the strain in the E3 direction, we have a value of that. That's actually strain 3, 3. So what I can do is I can put this bad boy into matrix form. I have my new, and I'll suppress this to get make it look a little bit cleaner. I now have both my stress vector, which is the first output, and then I have my strain vector. And if I look at them, again, they're going to be functions of x1 and x2 in both of them, which is, of course, what you're expected to input into your assignment. So I'm going to scroll up a little bit. The defined stuff I'll leave. I'm trying to get to a place where I can show you guys kind of the beef of the code, which will be this right here. So this is how you guys do it. And this is where I'm going to end off in the Mathematica tutorial because the video is getting a little bit lengthy, but I hope it helped. The part C and part D, again, those are just going to be the components of our stress vector. Von Mises stress, you now have your full stress vector, your full stress tensor. You guys can easily find the von Mises stress. If you guys wanted to plot a component of it, it's fairly simple. If I wanted to plot, say, sigma 1, 1, I'm just going to go contour, if I could spell right, contour plot, and then again, the contour plot is what I want to plot. Well, this would be my stress tensor component sigma 1, 1, and it's of course going to be, all right, well, where exactly do you guys want to plot it from? So we're going to say, well, x1 is going to be the length of the plate, so my plate starts at 0, it goes to 4, x2 would be the height of my plate. So again, that starts at 0, but this time it goes to 1. If I were to run that bad boy, I have a nice contour plot of my plate. And of course, it doesn't have any labels on it. We just have the dimensions of the plate. So if I really wanted to add something else, I can go contour labels, and then I have that little arrow and true. So contour labels true. If I run it again now, I actually have labels, so I can say, okay, well, sigma 1,1 is more extreme on the right-hand side, it's less extreme on the left-hand side, etc., etc. And I can do that for any one of these stress components. So if I wanted 2,2, let's just swap in 2,2 there. So when I run 2,2, it's, wait a second, Clayton, it does not exist. So a lot of people will actually start messaging me now, freaking out, saying, wait a second, Clayton, I have my stress tensor, and if I look at my stress tensor, there is a 2,2, it's right here, but it says it doesn't exist. And that's because you guys used matrix form on it, and if we use matrix form, it basically transforms it into a single variable. So if I were to delete that matrix form right there, suppress it, run it again, I'm good to go. So if you guys are looking at the contour plots, I highly recommend that you take away the matrix form of your strain and your stress tensor. It'll allow you guys to plot it much more efficiently. So that's it for question number 6. Again, a very, I guess, question number 4 of assignment number 6. Beefy video, but I feel like if I go in depth in the Mathematica code, hopefully it makes your guys' lives a little bit easier, which is what I'm going for. So thank you guys so much for listening. I really appreciate it. I will see you guys in assignment 7.